we get the 2 to the power of 1. So we get 2. Last one, ya, yang terakhir itu 1. So we figure out that this 27 can be expressed in the sum of 2 to the power of anything, ya. Okay. So the general idea is to repeatedly subtract out the largest power of 2 less than the number. Okay. You cannot subtract 2 to the power of n twice for any n. So it must be distinct. Yeah. You could have subtract 2 to the power n of n plus 1. So eventually we reach 0. The number is then the sum of the powers of 2 that we subtracted. Okay, let's try to formalize this as a proof. So we use proof by strong induction. Yeah. N is the sum of distinct powers of 2. We prove that Pn is true for all natural numbers. So we prove the base case. So we prove that the base case is true because 2 to the power of 0, ya, itu bisa, ya, 0 itu bisa can be resulted uh, by the empty sum of no powers of 2, yeah. So for the inductive step, assume for some non-zero n element of natural number that for any n prime, yeah, which is less than n, p n prime holds, and n prime is the sum of distinct powers of 2. So instead of showing n plus 1, yeah, we show that Pn prime, okay? We show that Pn prime, okay? So let 2k be the greatest power of 2, which is less or equal to n, yeah? Consider n minus 2k, yeah? So the key step here, n minus 2k is less than n, yeah? So we can prove with the n minus 2k. Okay, since 2k to the power of k is less or equal to n, we know that 0 is less or equal to n minus 2k. Okay, so we see the by induction, yeah. Okay, n minus 2 to the power of k is the sum of the distinct powers of 2, yeah. So we use the fact that any smaller number can be written as the sum of distinct powers of 2 to show that n minus 2k 2 to the power of k can be written as the sum of distinct powers of 2. Okay. So let's state another set, yeah, as set of the powers of 2, yeah, and is the sum of the elements of S and 2K, yeah. So jadi S itu adalah penjumlahan dua pangkat selain dua pangkat K, okay, selain 2K. So if we can show that 2K itu bukan elemen dari S, ya, is not an element of S, so we will have that N is the sum of distinct powers of 2, ya, namely the element of S and 2 to the power of K. So Pn will hold and completing the induction. So we show that 2k, yeah, is not element of S by contradiction. Yeah, we assume that 2k is element of S. Yeah, we prove by that contradiction. So, okay. So this might be very, very confusing because so we put a proof inside a proof. Yeah. Okay. So since 2k element of S, and the sum of the powers of 2s in S is n minus 2 to 2k. Yeah, we say that 2k. Yeah, 2k is less or equal to n minus 2k. Thus, 2k plus 2k is less or equal to n. How to do this is uh, by adding 2k into two sides, yeah. 2k plus 2k and then n minus 2k plus 2k. Okay. So 2k plus 1 less or equal to n. Yeah. This contradicts that 2k is the largest power of 2 no greater than n. So we have reached a contradiction. So our assumption is wrong and 2k is not the element of S as required. Okay. This is very, very confusing, right? So please try to learn this by yourself. Yeah. Here, I have tried to describe it to you to make it more clear. Yeah, to make it clearer. But you must learn by yourself. Yeah, untuk for understanding all these steps. Yeah. So the main point here is uh the n prime is actually the n minus 2k here. Okay. The n prime is here. Okay. Please walk through it by yourself ya. Ini adalah n prime yang dimaksud. So we want to prove that Pn prime is true. Ya. To prove that Pn prime is true, we must show that 2k here, ya ini ada 2k ya, 2k. The 2k here is not the element of S. Yeah. What is S? S is all elements of 2, is all the powers of 2 that is not including 2k. Ya, yang tidak mengandung 2k. Ya, jadi kita ingin membuktikan apakah 2k itu adalah the largest power of 2 that is less than n. Ya, apakah 2k ini adalah angka terbesar yang kurang dari n? Oke. Oke. So next we use another application which is continued fractions. Yeah. Continued fractions, there are a lot of continued fractions implementation. Yeah. So continued fractions mean that every denominator uh, can be expressed as a fraction. Yeah. So let's see here. Yeah. 1 plus half can be expressed as 3 per 2, then 2 per 3, 14 per 3, and so on. Yeah, we can get 3 over 14. Okay, so these are another example. Okay. So continued fraction is either an integer n or n plus 1 over f, where f is a continued fraction. Yeah. So every rational number, including negative rational numbers, has a continued fraction representation. Every irrational number has an infinite continued fraction representation. Even harder result, yeah, if we truncate an infinite continued fraction for an irrational number, we can get progressively a better approximations for of that number. So let's try to implement this to the pi, ya. Pi, kalau dibulatkan jadi 3, ya. So we have 22 per 7, we got 3.14, ya. Okay, we have another, we continue the fraction. We continue the fraction again. So lastly, we got the nearest approximation of pi. Ya, maksudnya adalah kalau kita lanjutkan fractionnya, makin lama makin kita bisa mendapatkan angka pi yang lebih mendekati angka aslinya gitu. Okay, so more continued fraction. Here we have 3 and 14, yeah. And we divide it by the ratio of 2 by 3 and then 1 by 2. Now we get these fractions. Yeah. So this called they call this procedure as anti-pyresis. Okay. Let's see another continued fraction, 2, 3, 5, and then 8, yeah, 13, 21, 34, yeah. Each fraction is the ratio of consecutive Fibonacci number, okay? So if anyone knows about golden ratio, yeah, so this also a continued fraction, yeah, the golden ratio. We have the ratio of 21 and 34, and then 21 and 13, and then 8 and 13, and then 8 and 5, and then 3 and 5, 2 by 3, 1 by 2, and so on. So we can get a beautiful golden spiral. So the aim is to prove that all rational numbers have continued fractions. Okay, so let's see. We can just use any random rational number, yeah. We can get that any uh any rational number can have a continued fraction, yeah. See here, they have a continued fraction, and it is always the first fraction always be larger than the last fraction. So it is sequentially greater than the next steps. So here is another golden ratio. Yeah. So we use the division algorithm. Yeah. So for the division algorithm, so we have integers a and b with b greater than 0. There exist unique integers q and r such that a equals to q multiples b plus r. What is q and r? Ya, q itu sebenarnya adalah pengali ya, quotient, and r itu the remainder or sisanya gitu. So we got r between 0 and b, yeah. Okay, so given a equals to 11 and b equals to 4, so 11 equals to 2 times 4 plus 3. Okay, so please read and learn this theory, the proving of this theory by yourself, yeah. Okay, uh, please read it through and walk it through, yeah. Because our credits might not be enough to learn this in the class, yeah.